Okay, hello everybody, welcome back, and we will continue with the second part of the lecture. Thanks, Aurora, and the space is yours.
All right, great, thank you. I think before or right at the end of the stream, somebody had asked a question about when the most dominant source of broadening, or when you need to care about each type of broadening and which type of broadening dominates. So let me quickly talk about that. Just share my slides again. Okay. Yeah, so for all the different types of broadening, so it depends on what type of star you're looking at. So for thermal broadening occurs in all stars because all stars have a temperature and they have a random distribution of particles. And so thermal broadening kind of like sets the base broadening for a lot of stars. Natural broadening is really doesn't usually contribute to much broadening. So all stars will have thermal broadening and natural broadening, but thermal broadening usually kind of sets the base amount of broadening. And then on top of that, it really depends on the type of star that you're looking at. So if you're looking at very dense stars, so like white dwarf stars, or even like M-dwarf stars, pressure broadening can be a significant amount of broadening. So right, here's our spectra, and I think the most common case for pressure broadening that you're going to see a difference is looking at white dwarf stars versus main sequence stars versus giant stars. And you can tell the difference between those type of lines if you have very large changes in pressure. So main sequence stars oftentimes have surface gravities, so we measure this in log G. Surface gravities of log G of about 4 or something like that, where a white dwarf star will have 2 orders of magnitude or more larger log G. So it'll have a log G of 6 or higher. So that's 2 orders of magnitude, whereas a giant star will have 2 orders of magnitude smaller densities. So log Gs of about 2 for giant stars, and can even be lower for supergiants. And so, yeah, you're going to notice a difference in pressure broadening, but only with a change in surface gravity of like 2 orders of magnitude. And then for rotational broadening, you're going to need the star to be rotating extremely quickly to measure rotational broadening. So for the sun, for example, we have the sun has a 33-day rotation period. And so a spectrograph that has a resolution of 50,000 can resolve velocities usually around a few kilometers per second or something like that. So the rotation period of the sun is not going to show up. You need rotation periods on the order of a day or less to see rotational broadening. And the stars that are going to have rotation periods of a day or less are usually younger stars and are either A-type stars. A-type stars often have extremely fast rotation periods, or M-type stars, so very low mass stars. So this measurement here is from an M-dwarf star. And M-dwarf stars, a lot of them are rotating with periods of less than a day. And A-type stars can have rotation velocities of like 100 kilometers per second. So it's really easy to measure that when your spectrograph has a resolution of a few kilometers per second. So yeah, young A-type stars and young M-dwarf stars are where you should worry about rotational broadening. For main sequence sun-like stars, usually you don't have to worry about rotational broadening. And then Zeeman broadening, like I said, you need to have a star with extremely strong magnetic fields. So magnetic fields that are like 3 times stronger than the sun in order to see any Zeeman broadening. Sorry, 1,000 times stronger than the sun, 3 orders of magnitude. Because in our example here, we have kilogauss scale magnetic fields. And my area of expertise is low mass stars and exoplanets. And low mass stars, so M-dwarf stars, can have surface magnetic fields that are measurable with Zeeman broadening. I'm not exactly sure what other spectral types they've measured magnetic fields on, but I know that they've measured them on low mass stars pretty effectively. So again, yeah, it depends on what type of star you're looking at and what you know about the star. And that will tell you what type of broadening is going to be the dominant source of broadening. Okay. So yeah, like I said before, I have a bit longer of a practical part or the workshop part of the class. So this is all I have for the lecture. So I'm going to do a Kahoot quiz. And then after the Kahoot quiz, we'll take our break and come back a bit earlier than normal. So let's see. Let me just start the Kahoot quiz.
Excuse me, Aurora, you have a question here in the chat.
Okay, I'll do that before.
It says, what determines the depth of the absorption lines?
Okay. Yeah, so the depth of the absorption line is determined by, a bunch of different things. Mostly just how abundant that element or molecule is and what energy state it's in. So let's go back to the slides again. Let's go back to our example of the A star. Okay, yeah, so for our A star here, For our A star here, you can see that it has really deep hydrogen lines. And so the depth of those hydrogen lines is going to depend on how much hydrogen is in the n=2 state. If we're looking, so in particular, this is H alpha. This is the n=2, the transition from the n=2 state to the n=3 state, and it's at 656. The rest of these are Lyman lines, so they're from the n=1 state. And so, so the depth of the line is going to relate to how much of that element is in the particular energy state where it can have that transition. So it's a combination of the temperature and how much of the element is in that particular energy level, and also the abundance of that element. So then for hydrogen is just so prominent, and there's just so much hydrogen that the depth of the line is mostly just determined by the temperature and this balance between ionization and excitation. But metals, there can be differing levels of metals. So for metals, anything larger than hydrogen or helium, it's a play between how much of that element is in the atmosphere So you can have more oxygen than, some stars have more oxygen than others. Some stars have more iron than others. And then also the same type of thing where you need the correct balance of energy levels and ionization to get that absorption line. Okay. Yeah, let me know if you have any other questions. Those are some good questions. Okay. I will just move on to the Kahoot quiz, but I'm happy to answer more questions after the Kahoot quiz. Okay. Great. So you can go to kahoot.it and enter the game pin, which is 5274430. And we will start the Kahoot quiz.
Aurora, sorry to interrupt. You're sharing us the wrong window.
Oh, sorry.
It's okay, no problem. You're showing us, in fact, that almost the solution, I guess.
Oh, no.
No, it's not true.
Okay. Is that the right one?
Yeah, that's the right one. Thank you very much.
Okay, I'm going to wait 1 more minute since we just had some more people join. Okay, nobody's joined for a bit, so I think that we will start now. Oh, we had 1 more. Great. Okay, let's start. What kind of spectrum will hot diffuse gas make? Will it make a continuous black body spectrum, an emission spectrum, or an absorption spectrum? And to clarify, by diffuse, I just mean like optically thin, not dense. Okay, nice. Yeah, so most of you got this. Hot diffuse gas, so hot optically thin gas, will make an emission spectrum. You want if you want in a black body spectrum, you need hot optically thick or dense gas. And for an absorption spectrum, you need dense gas, and then on top of it, you need this diffuse gas, and that will make an absorption spectrum. Okay, true or false? An M-type star will emit more of its light at blue wavelengths than a G-type star. Okay, great. Seems like most of you got this one also. An M-type star is the cooler spectral type, and so it will emit more of its light in red wavelengths. A G-type star is hotter than an M-type star, and so it will emit more of its light at bluer wavelengths. So next, according to this plot, at what temperature would you expect the strongest H alpha? So H alpha is n equals 2 to n equals 3 absorption. 5,000 Kelvin, 10,000 Kelvin, 15,000 Kelvin, or 20,000 Kelvin. Okay, yeah, so I wish the plot was back. But we would expect the strongest H alpha absorption around 10,000 Kelvin, because at temperatures that are hotter than that, the single electron of hydrogen is ionized. But at temperatures cooler than that, the electron is in the ground state, the n equals 1 state. And so we need the electron to be in the n equals 2 state in order for it to transition from the n equals 2 to the n equals 3 state. So nice job. All right, next. What is the spectral type of this spectrum? Hopefully you can see this, and it's not too small. But the choices are an O-type star, an A-type star, a G-type star, or an M-type star. All right, yes. So what should have given you a hint for this spectrum is that it seemed to go up. So we got more flux as we went to redder wavelengths. So that means that the spectrum is cooler. And also we saw lots of molecular absorption. So these broad, deep absorption features. And molecules only start to form in very late K stars and M stars. So anytime we see molecules, we think cool stars. And anytime that we see more redder light, we also think cool stars. So M-type stars are the coolest type of stars. Okay. What makes most of the spectral features in brown dwarf stars? Or I guess they're not stars, in brown dwarfs. Absorption from titanium oxide, absorption from methane and water, absorption from elements like hydrogen and helium, emission from elements. Okay, so this was a little bit of a tricky question because I had absorption from two different molecules, and I didn't talk about this too much in depth, but it did seem like most of you chose the absorption from the molecules, which is good. So at lower temperatures, most of the features are from molecules and they're not from elements. So hydrogen and helium, we don't see too much absorption from things like that in the brown dwarfs, which are even cooler than stars. So then you had to choose between titanium oxide and methane and water. And did briefly show the plot of the brown dwarfs, and most of them had methane, which is CH4, and water, H2O absorption. And the titanium oxide answer is a bit tricky because titanium oxide is the main feature in M dwarfs. But by the time we get to cooler brown dwarfs, actually we don't see any titanium oxide anymore. Nice job for the molecules bit, though. Okay. True or false? Pressure broadening results in Gaussian line shapes.
Hi, Aurora. Excuse me to interrupt, but you have your microphone off. Yeah, everything you said, we didn't listen.
Okay. I was just going to say that pressure broadening and natural broadening results in Lorentzian line shapes, whereas turbulent broadening and thermal broadening and rotational broadening, those are all Gaussian line shapes. Okay. Okay, so which of these A-type stars will have the broadest lines? A white dwarf, a main sequence star, an asymptotic giant branch star, so a giant star, or they would all have the same lines. And so, yeah, you don't assume anything about their rotation or anything like that. Assume that they have the same rotation speeds. Okay. Yeah, so assuming that they all have the same rotation speeds, then the thing that's going to change between all of these stars is their pressure broadening. Since they're all A-type stars, they all have the same temperature, so nothing's going to change about their thermal broadening. And the white dwarf star has the largest pressure, and so it's going to have the broadest lines because of pressure broadening. All right. If you measure H alpha in a star to be at 653 nanometers, what direction is the star moving? And the hint is that normally H alpha is at 656 nanometers. So is the star moving away from Earth, towards Earth, tangential to Earth, or it's not moving? Okay, great. Yeah. So if the star has a H alpha line that is a blueward, so at a smaller wavelength, then a blue shift, according to a Doppler shift, is moving towards us. So most of you got that. That's great. And we're going to go into radial velocities. That's what we're going to spend a lot of time on tomorrow. But I just wanted to get you thinking about Doppler shifts and stuff today. Okay, so which of the following would result in a large rotational broadening? A rapidly rotating star with a rotation axis along the line of sight, a rapidly rotating star with a rotation axis perpendicular to the line of sight, a slowly rotating star with a rotation axis along the line of sight, or a slowly rotating star with the rotation axis perpendicular to the line of sight. So the rotation axis is the axis around which the star is rotating. Great. Yeah, so larger rotational broadening results from more velocity. So a star that's rotating faster is going to have more velocity coming towards us and more velocity going away from us. So that means that the line that's normally deep and narrow is going to be moved shorter and wider. So that's larger rotation velocity. And this has to also do with our line of sight. So a star that has the rotation axis directly along our line of sight, the star is going to be rotating this way. And so none of the actual velocity is going to be moving towards us or away from us. So we won't be able to measure it. So we need the rotation velocity perpendicular to our line of sight. So the star is rotating this way. Okay. So this is the last question. What causes Zeeman broadening? Is it caused by rotation? Is it caused by high pressures? Is it caused by high temperatures? Or is it caused by a magnetic field? All right, great. Yeah, Zeeman broadening is caused by the magnetic field. All right, so that's the Kahoot quiz. Nice job, everybody. I feel like everybody got most of the answers. So that's great. Okay, so let me stop sharing my screen. So next, next we're going to be doing the workshop part of the course. And let me just show you, hopefully. Okay, hopefully you all got something that looks like this. This is the workshop that we'll be following. This is the worksheet that we'll be following for the third workshop. And during the break that we have coming up, it would be great if you could go to the GitHub link and download a few of the spectra that we need. So we need both of the files that have file names beginning with ADP. So these are two different HARP spectra. And we need that for the first part of the workshop. And then for the second part of the workshop, you're going to need the Carmenez spectrum of WASP-33. So that's labeled with CAR dash and a bunch of things. And then a model of WASP-33 that I've also put in there, and that's just called WASP-33 model. And for today's workshop, we're going to be using the co-laboratory again. So hopefully you got that working on the first day. And if you want to follow along, you can use the same example for how to open the files from the first day, and the link is here. And then I'll be showing you a few things at the very beginning for how to open the files again, but for the most part, we'll just be going through these examples. So I guess we ended about 5 minutes early.
Yes, we are 5 minutes ahead. We have no questions so far on the chat. And if you think we can reconvene, it is supposed to be at 10:25, but we can do it at 10:15, so 4:15 your time. And we can have a little bit more time for the lab in case you need to explain a little bit more in detail what they are going to do.
Yeah, I think that's fine. 4:15 works.
Okay, 4:15 your time, 10:15 Colombian time. See you all in 20 minutes. Thank you very much, and see you in a while.
Okay, bye.
Bye.